There we go. Okay, hello everyone. Welcome to Handmade Hero. This is day 5 of programming, and I was very excited to see everyone here. We have done a tremendous amount of work this week, actually. Despite only having an hour a night, we now have our very own animated graphics on the screen in Windows that we wrote entirely ourselves, which kind of opens the door for us doing absolutely anything we want to do. So, for those of you joining us who may be new, this is Handmade Hero. This is the the weeknight series. You can go to handmadehero.org and see. This is the weeknight series where we code a complete game from scratch, no libraries, no engine, just us, and we see how absolutely everything works, which has been a lot of fun, and I am looking forward to doing even more of it. So you can go up here on handmadehero.org to find more information about it if you would like to, and if you have questions or anything for me, there's an email a question button, and if you would like the source code, you can always pre-order the game, and it comes with the source code that we upload every night. All right, so let's get started. Today is a Friday, so we are going to be doing some recap about the things that happened this week. And basically, we spent the first day, Monday, was not a very interesting day. We basically just set up our development environment. And Tuesday through Thursday, we got animated graphics on the screen, which was pretty cool. And so let's open up that file here. We basically put it all in one file. And one thing that I'd like to point out is there is not very much code here. It is really pretty straightforward, which I think is pretty great. Because one of the things that often intimidates people is they think that if they write everything from scratch, it's going to just be a huge amount of work. But it's not. There is very little code here, and we have done it in 3 nights with mostly me explaining things. So if you were to do this yourself, I think it would take you 10-20 minutes to put in some code like this. It is really not much code. What I'd like to do tonight is I'd like to kind of step through this and just really emphasize how every last little thing works so everyone can be on board with that. And maybe we'll try to start question and answers a little bit early if we do have time for that so people can get drill downs into the things that they want. But before I get started, I wanted to clear up just a few things from emails during the week. So first of all, I wanted to thank I don't even know how to pronounce your name, I'm sorry. It's something like Kurt Karteltepe for writing in because we did not need to order a capture card at the end of the day. It turned out that really all we needed to do was change OBS from monitor capture to the secret other monitor capture option. And I tested this, and it turns out that, yeah, if you switch it into this other mode where instead of capturing monitor, it's capturing a game, but you select the monitor as the game, suddenly everything works, and I didn't have any more problems like I was having, like the disaster that happened last stream. So thank you very much for solving that problem for us. That is way better than getting a capture card because the capture cards was looking like they were a bit of a nightmare and had a bunch of drawbacks that I didn't want to deal with. So this is perfect. We are running smoothly, and I think everything will go well from now on, hopefully. Anyway, I also wanted to thank Martin Vladik for writing in. Again, don't know how to pronounce your name sometimes because I wrote a thing here which was saying, let's check if HRedraw, VRedraw, and OwnDC still matter. And if you remember from the original part of the stream, we were filling out a win class structure here. And if you go back to the documentation and you look at the win class structure, although we deleted it because we were just seeing if it would do anything, in here you can see that there is a style field. And the style field, we had put some stuff in it. We had put in, oops, that's a lowercase style, not a capital. We had put this in there. And basically they were a bunch of styles. We ordered them together to set them all. And I was sort of hypothesizing, it's like, what exactly do we need these for? HRedraw is basically something that says redraw the window when you size it horizontally, and this is redraw the window when you size it vertically, and this is whether or not you have your own DC. We pretty much determined we don't need our own DC because it didn't really amount to anything that we would need to do. But it turns out that HRedraw and VRedraw are actually pretty good. Martin Vladik wrote in and tested them for us just to verify. But basically what it does is it's really just a flag that says I need to repaint the whole window when I resize it, not just the section that's new. So if I make the window a little bit bigger, instead of just painting the new section, I want you to have to repaint the whole thing. And what he pointed out was he was like, well, if we're going to be stretching our image to fit the window or anything like that, we're going to have to redraw the whole thing, so we probably do want those in there, and he tested them to make sure they work. That was great work. Thank you for doing that exploration, and I think you are totally right on the money. So I'm going to consider that matter closed and say that we do want these 2 flags, so we are going to leave them in there. All right, that is it for my thank yous. Now I want to address just a quick little optimization thing. It may be a little bit early to talk about this, but I'm going to talk about it Anyway, one of the things that I did when I wrote this function, Win32 update window, is I passed a pointer. So basically we had a rectangle when we called Win32 update window. And if you go look at where we actually called that, you can see that I got the rectangle. It was on the stack here inside the WM Paint message, and I went ahead and passed a pointer to it. Now the reason I passed a pointer to it was a bit of a habit. Usually I tend to pass pointers to things if the structures get large, and this is a 4-element structure, so maybe it's not that large, so it's a little bit weird that I did it, but you know, force a habit, sometimes old habits die hard. And one of the things that someone pointed out when they wrote in, and it's a good point, is that typically one of the things that you want to try to avoid is passing pointers to things that are on the stack if you can avoid it, because the compiler now no longer really knows what's going on here. Because basically what happens is if the compiler sees something like this, where it's going to get the whole rectangle, the whole thing will be passed fresh to the function that is going to use it. There's a bunch of assumptions it can make. It can start to assume that nobody else is going to need to touch that thing. It can assume basically that it is just a private copy that this thing is going to use itself. There is no possibility for aliasing. There's no possibility for anything. What aliasing is basically something we'll get to a little bit later, and it's something you probably don't need to worry about too much right now. But basically it's just saying whether I have two pointers that might point to the same memory. And the reason that is important is because when the compiler is compiling your code, you can imagine if I have something like this where I've got two pointers, let's say, right, A and B. If I was, and these are pointing to something, this is pointing to memory, both of these are pointing to somewhere in memory, and we don't actually know where they are, let's say, and neither does the compiler. They're just some pointers, maybe they were passed into this function, we don't know where they came from. So if we have these pointers, and I'll take them out of the function just so we're not thinking about it in this const function, we're just saying somewhere in our code we end up with pointers A and B. Well, one of the things that can happen is I may want to write to A. I may want to go ahead and write something to A, right? And similarly, I may want to read something from B, right? I may say that, you know, I don't know, some other thing here, int x equals star B, or int y equals star B, right? Now, if you take a look at this code for a minute, it looks pretty obvious what's going on. I'm going to, oh, well, you know, I should probably even read out the values that they are, but point being, I can upcast integer, that's fine too. Anyway, I'm going to read out of here 8 bits and shove it into these 32 bits of y. It's going to look at whatever is in the location pointed to by B, and it's going to put it in Y. And then I'm going to go ahead and I'm going to write 5 out, just the 8 bits that represent 5. I'm going to write those out to wherever A is pointing to. And then I'm going to reread B, right? Just going to reread the same thing. So at the end of this, we are all looking at it and we say, well, obviously, right, Y and X are the same, right? Because here is the pointer to B. We're reading it twice. It should be the same. So duh, the compiler should just load it once, right? It should just turn that into this so it doesn't have to go out to memory 2 times to find out what that is. It should be efficient, right? Well, the answer is it cannot do that. And the reason it cannot do that is because we have not given the compiler enough information to know that A does not point to the same location as B. So it could be that this write to A right here, this write of 5, overwrote the previous value that was in star B, because if the pointer, I mean, if somewhere outside of here, before we got to here, if someone had done A equals B, well, then this code just reads and writes from the same location. So this will equal 5, right? But this will equal whatever was actually there before we wrote the 5. Right? Makes sense? Everyone on board with that, I hope? So that is called aliasing. It is a situation, well, it is one type of aliasing. There are actually a lot of types of aliasing, but that is pointer aliasing. That is what happens when you have 2 pointers that could point to the same thing, and the compiler does not know. So there are ways you can actually mark up your code to tell the compiler things about the fact that there is no aliasing, and there's various stuff like this. But one of the easiest ways to do it is to just not use any pointers. So if you can get pointers out of the equation entirely, sometimes that's more effective. And one of the things that you'll note about this function is it is small. It is a very small function. It is a classic candidate for what's called inlining, which is where the compiler will go, hey, there is not much work being done here. Maybe instead of actually generating a whole function for it, I will just go to the place that it's called and I will just shove the code right actually in there. And if it's going to do that, that's pretty handy. It can go ahead and look at this and know that it's not, it can inline it and know that it's not actually a problem to go ahead and assume that this client rec stuff is all the same. And you may be asking, and it's totally legitimate, Casey, if it's going to do that, if I just have a star here, why isn't the compiler smart enough to figure out that, hey, it's just a pointer, we're not changing the pointer, there aren't 2 pointers, what's going on, why do you think there's aliasing there? Well, the answer, and you should definitely defer to people who work on compilers for this sort of thing. The answer is that actually what the compiler ends up seeing at the end of the day isn't something quite this simple oftentimes. Oftentimes the optimizer happens at the end of a bunch of things that occur inside a compiler. It basically turns things into stuff like bytecode or pseudocode, different things called IRs, intermediate representations. The code goes through a bunch of transformations, comes out the other side, and then the optimizer gets this big, goopy mess. That is just the way compilers work. There's a number of reasons for it. You might argue it's a bad idea, or you may say that it's a good idea, but either way, that is what's going on in a lot of compilers. And so at the end of the day, this will probably not actually look so clean to the optimizer. It'll look like a bunch of different things. It'll actually look like 4 different memory locations, left, top, right, and bottom, that all came in here at the top of this code, and it has to sort of go back and do memory partitioning to go, oh, that's what's going on. There's a whole bunch of stuff that happens. So I don't want to belabor that point too much. Largely because I am not an expert on optimizing compilers by any stretch of the imagination, and I am probably going to explain them poorly if I try to give you specifics. But point being, one thing you can do to help the compiler out is if you are passing relatively small things and you could pass them by value. Nowadays it is probably a good idea to do that, whereas in the old days it probably wasn't because there wasn't as much compiler optimization stuff going on. Nowadays there is, so probably we should have just done that. Someone wrote in to suggest that we do that, and I think that's probably a good suggestion. I oftentimes pass things by value a lot of times, and that is probably a good one. So I say we go ahead and make that, but one thing that we could do in the future is we could look at the code to see what the difference was. In this case, it's not performance critical, so I don't think we really need to do that, but it's just something to consider. Okay, now that we've gotten rid of that, go ahead and do that. Now that we've gotten that out of the way, I have one more email that I thought was good to go over that someone sent in. Basically what they were asking, they were following along at home, which is awesome. The number of people following this series along at home has been surprisingly large, and that is awesome. To all of you out there who are typing while I am typing, that is just totally cool, and I love all the stuff you guys have been trying and sending me questions. It's been awesome. Anyway, what they mentioned is they said, hey, when I was following along, I accidentally put this definition, the MSG, the message structure, I put it out here. Instead of putting it inside the actual run loop, I put it out here. And what he was asking is essentially what is the difference? Like what difference does it make to the actual code that gets generated where I put this? And again, that is an awesome thing to ask. That is exactly the kind of thing that I hope people are thinking about, because that is the kind of minutia that you want to learn, because once you learn it, you know it forever, and now you just have so much better idea of what kind of code is getting generated. And nowadays, people are very detached from the actual stuff the CPU is doing. And again, one of the things I really want to hammer home is it's great to stop that, to actually go and reach down and really figure out what's going on. It makes you such a much better programmer just to know. Anyway, the difference is essentially nothing. You will be heartened to know that most compilers, as far as I am aware, are pretty smart about how they lay out things on the stack. Now, basically what happens is when we come into this function, again, if you saw the intro to C stream, there is a stack, and the stack is basically something that is a block of memory that is reserved for our program as it runs, and it grows on the top and shrinks every time we call and return from a function. So we call into a function, it pushes onto this stack, it basically puts on the values that we pass to the function, and it puts on the values that that function needs for its local variables. So when we declare something like a local variable, like this win class here, like these integers, and like that message structure, it is basically just growing the stack out to make room to store that. So instead of actually doing an allocation, remember we did a virtual alloc up there to alloc a block of memory. Instead of doing an allocation, which is something that'll sit around for a while, it's just putting it on that stack. The stack kind of grows and shrinks, and it's just memory that ends up being reused. You can think of it almost, like a watermark. It's like we've got this pool. We've got this big old swimming pool, and it's empty when we start the program, and the water level rises, and the water level shrinks, and the water level rises again, and we're just using that big empty space. We're using the same space over and over again. So when you call into a function, it uses space on the stack to store the local variable, store the parameters that it uses, that sort of thing. When you return from that function, it backs up the stack to point, it no longer is using that area. But then the very next function you call will reuse that same area that was used by the previous function, right? So it's constantly getting reused, the stuff on the stack. So the question of what happens when I declare a new thing like this is basically that it's largely for your convenience where you put it. When you put something inside a while loop, what that means is nobody can reference it outside the while loop. So the reason that I put it there was because basically I didn't want people out here, I didn't want people maybe who were going to be, let's say someone right here, I didn't want them touching this. I didn't want them doing stuff to message in here. That's no good, because message is only supposed to be something that's used as basically the only reason we have it in the first place is to get a result from peek message. So I certainly don't want them using it out there, and I definitely don't want them using it down here, which they could also do because it was declared up here. Remember, it is in this outer scope, this scope right here. So anyone in that block could use it. And so basically what I'm doing when I put things inside particular blocks and functions is really I'm just trying to make sure that they are sort of lexically scoped, meaning the people who can refer to them lexically scoped as narrowly as possible to avoid people accidentally referring to things that they should not be. And while it seems like that's an odd thing to protect against, it actually is kind of useful because oftentimes code gets moved around and cut and pasted in various ways inside a function. And you may accidentally leave something that kind of moves to some place it shouldn't, and now you've got a bug. So it's just helpful to kind of put that in there. It helps the compiler catch a few mistakes for you. No big deal. If not, a lot of people who program in straight C put all their variable declarations at the top because that, C does not have declare anywhere until C99. That's a habit some people got into, and so on and so forth, and that's totally fine. So you can certainly be a very productive programmer without doing that, but it's something to consider. So when you put it anywhere, doesn't matter where you put it, basically all that's going to happen is the compiler at its discretion at some point during the execution of this function, whether it's at the beginning or right when it sees it or any time like that, is going to enlarge the stack to hold it. That is the only real requirement, as far as I'm aware, that the compiler has to adhere to. It has to be able to do that, but it can do basically anything it wants to do to optimize it. So you don't have to put it out here to prevent it from basically growing and shrinking the stack all the time in here. An optimizing compiler, I should think, would be plenty smart enough to make sure that it can always just do that allocation, knowing that it's always going to have to happen, do that stack grow up at the top, and make it nice and efficient. So you can put it in there, and I don't think there's really any penalty. Now, it's worth noting that in C++, if you are going crazy with your C++ness, there is another thing to watch out for. And what that thing is that individual structures, classes, those sorts of things, they can have constructors and destructors. And what constructors and destructors are things that happen when something comes into existence and when something goes out of existence. They're basically function calls that are triggered on those boundaries. And if you had something in here, like the message structure, if that had a constructor or a destructor, the definition of what the compiler has to do is it has to call the constructor when it is created, and it has to call the destructor when it is eliminated. So in that case, there would be something additional to think about. Putting it inside this while loop means that every time through the while loop, it would call the constructor right here, and it would call the destructor right here at the end of the scope. That is the compiler's responsibility. It does not have the flexibility to do anything else unless it can determine that it can safely defer that destruction in some way. It pretty much has to do it. That is the specification. And so there is a real difference, potentially even performance-wise, between that and this, if there was a constructor call, because that constructor call could be expensive, and the compiler is now doing something else in the loop. It is not just a case of it having to reserve space for this somewhere up here and just using it when it gets down here. It's not just lexical scoping. That is actually creating real program behavior. So that's something to be aware of. We will almost never be using anything like that in this stream, but a lot of programmers do use those sorts of things, so be aware of it. Okay, hopefully that answered that question pretty well, and we are done with the questions from the email. Now, one more thing for those of you who are following along in my .emacs file. If you look in my .emacs file in here, we've got .emacs in the MIST directory. I set my font to Liberation Mono. That is the font that I load. And it turns out that that is not a font that is often on machines by default. So if you would like to get it, if you're trying to follow along with my Emacs file directly, you want to type Liberation Mono into your Google search, and you can go on here to the Red Hat page and you can download it. That will prevent you from getting an error in the .emacs file. So I would redistribute the font, but I don't know if that's technically allowed, and I want everything in this package to be distributable in the public domain, so I am not going to include it, but you can go get it yourself. Alrighty. All that said, that is the entire cleanup for the week that I can remember. So now is the time for us to kind of look at this code and go a little more in depth from what we were able to do when we were actually implementing it. So, first thing I want to do is I want to look at these global variables. These global variables are not something that I really like to have around, like I was saying. The reason for that is they kind of get a little, it gets a little confusing to know who and when and where and so on they are being accessed. And you can do that, you know, if you want to, you can work around that actually. If you have global variables and you like to use them, there are ways to work around that. You can do things like come in here. If you have a cleanly compiling program, you can add some random character to the end of a variable and hit compile again, and that will show you all of the places that it was used, because you will generate errors in all the functions that reference that. So that is one way you can figure that out. But I would rather go ahead and bundle these things up into something that's a little bit more concise. Again, this is not for performance or anything like that. This is strictly because I would like to keep the code in a way that's a little more clean, a way that's a little more manageable, so that we can see easily, no matter who is looking at the code, exactly what had to happen for these bitmaps, for this off-screen buffer that we created that we're drawing the screen every time to exist. And so basically what I'm going to do is I'm just going to open a struct, and I'm going to go ahead and put this stuff in there, all the stuff that we actually needed. So we knew we needed a bitmap info to describe our bitmap. We know we needed a pointer to the actual bits of that bitmap. We know that we needed the width and the height, and I'm going to go ahead and remove bitmap from these, because since they're in a structure now, we're going to know that. So I'm going to go ahead and remove bitmap from those. We're going to have the width and the height there, and we are also going to have the bytes per pixel. And one of the things that's nice about this, you can see we bundle this all up together, and now we know that anyone who needs to operate on this bitmap, we can just pass this structure, and we're going to call this our off-screen Win32 off-screen buffer for now, because I don't have a better idea for a name, so that's what we're going to use. So basically, if I just bundle those things up, now anyone who has to use this can just get a pointer to one of these off-screen buffers, or pass it by value, as the case may be, and they're not going to modify it. And then they can go to town, and they know they have all the information they need, the width, the height, the bytes per pixel, and so on. So I'm going to go ahead and change our functions here to actually work on that. Now you can notice this is a render weird gradient. It will now take an off-screen buffer, and it knows to write to it. And you can see that we're kind of levering up. We've got a little bit more power here. The reason that we have a little bit more power is actually because now we could have multiple off-screen buffers. Before, when we had those global variables, well, if you did render weird gradient, it was always going to go into the same buffer, right? Same buffer. You could never have multiple buffers. But maybe we wanted multiple buffers for some reason. Who knows? Now we have the flexibility to do that, because every time we call render weird gradient, we're going to pass it the buffer to use, and we could have tons of different buffers if we wanted to. So again, that's a lot of the reason for pulling things out of global variables, for pulling things together, is it makes it clearer, and it also makes it more flexible. So the width and the height here, I'm just going to dereference into that buffer. And again, I don't know, this is a pretty giant guy. I don't actually know if I want to pass this guy by value. We could pass him by value because we're not really going to change him. So we could actually do it this way. And I don't know which one's better. You know what, let's do this. Let's actually go ahead and do that, since tonight is an exploration stream. Let's see what the optimizer does. Let's actually take a look and see what the optimizer does if we pass this by value, to see whether or not it does the right thing in either case. Okay, so I'm going to go ahead and pass that buffer in here, the buffer that's supposed to write to. And I will go ahead and change all of these things that have to happen. Bytes per pixel also coming out of the buffer now. The memory also coming out of the buffer. And that looks like just about everything. Let's see here. Yes, that is now clean. Looks like it's doing it. Now the pitch was computed, and this thing is operating off that. One thing that we could do here is decide that the pitch is also a variable, so we can have a little bit more flexibility with how we actually allocate that. So I'm going to go ahead and put that in there. And then I'm going to move the pitch computation down into here, because we're going to need that in a second. All right. So here is our off-screen buffer. We're going to render our weird gradient to it. And it looks like that's pretty clean. Let me compile. That should compile that cleanly. Oops, nope, got to get that out of the buffer as well. There's really no reason for me to dereference those buffer widths and heights here for referencing by value. We can just go ahead and do that. So that should be fine as well. And so that looks like a totally reasonable compile. Yes, so that is nice and clean now. Takes the Win32 off-screen buffer and draws to it. Now, Win32 resize div section, that is going to take our Win32 off-screen buffer as well. But this is kind of interesting and something to note. What we have to do here, since we are changing this thing in place, we have two options, ladies and gentlemen, two options that we can do. If we were to pass this by value, that basically means that we have our own private copy of it, yes? It means that when this function is called, we are getting a copy of an entire buffer that someone else was doing. Not the buffer memory itself, because remember that is just a pointer that's inside here, and a pointer is just 32 or 64 bits, depending on how we're compiling. But we get a copy at least of this entire structure. So that means, excuse me, I'm still sick today. That means basically any changes that we make will not stick. So you notice we're changing a bunch of things. We're going to want to change a bunch of things in the buffer here. Right? We are writing to all sorts of things in this buffer. We are changing the width. We are changing the height. We are changing the bitmap info structure. We are changing the memory that it points to, and we are computing the pitch. We are doing all kinds of stuff, right? And since that is the case, that means that when this buffer comes into us and we get a copy, if we go change that copy, well, the person who called us is never going to see those changes. They're just going to disappear because this is a local variable that's on our stack now, basically. It's a parameter to us. So what we could do is we could, if we were in functional programming style, we could return, basically, a new buffer to them. So we could just return buffer here. So that's a local variable, and we could return it, and they would have to capture that return. That's a little bit error prone, so this is not a particularly performance sensitive function, so even if the compiler was going to have an easier time optimizing something like this, I don't think I would prefer that. What I would prefer is a situation where basically it gets a pointer to a buffer and just modifies that buffer in place. That is much more what I would prefer. Now really what we want to do is we wish Chandler Carruth was watching this stream and he could tell us if that was a terrible idea or not. We basically need some optimizing compiler author to come in here and tell us how bad it is that we're doing stuff like this. But at the end of the day, like I said, this function is called so infrequently that we really just don't have to think about the performance implications of this, because it is called once whenever you resize the window, and that is all. So it is not even called every frame of our game. It is not going to be on the critical path in any way. So I'm a little more comfortable writing it that way. I'm going to write it that way for now. But yes, if someday, for some reason, Chandler ever does watch this stream, please tell us if we are being stupid, because that would be excellent information to have. So I'm going to go ahead and change these dots to the arrow reference because we have a pointer to a buffer, not an actual buffer. So I'm going to do that. And the other thing that I will note is we actually store the width and height in here. So if we were being super conscious about space, we would get rid of these. I don't think that's necessary because, again, we've got so much memory to play with at this point, and that is a tiny little bit of that concern. So I'm going to go ahead and just finish up the porting here. We got to go ahead and free the memory out of that. We have to allocate the memory out of that. Yes, indeed. All of that is good. And we have, oh, right, we changed that just to info. So I'm going to go ahead and change, oh, you know what? Everyone loves this so much in the stream, I'm going to do it again. Kill rectangle. I do not know why they like that so much, ladies and gentlemen, but they do, so we need to do it. You have to give the people what they want. That's my opinion on that. Oops, got to actually change that to buffer as well. And here we go, buffer width, buffer height. So again, I am doing absolutely nothing to the code right now. I'm just changing it to read out of that structure. And that is a little bit of an arduous process. I probably should have used a search and replace for this if I was smart. But what can you do? You think of things after they would have been good sometimes in programming. It happens. All right, so now we've got our resize set, and it will take a buffer to resize as well. And now we're going to go down here to Win3 update window, and that as well should now basically be, instead of update window, I think we're going to call that Win32 copy buffer to window, because that is what it is actually doing. Or maybe I will say display buffer in window, something like that. I don't know, whatever you like to call it. It is your code if you are typing in at home, and you have the control. You have all the control over what is going to go on. Do not let me brainwash you into typing in the names that I like. All right, so this guy, again, we're not going to change the buffer, so we could go ahead and pass by value there, so maybe we'll go ahead and do that. And let's go ahead and change the width and height to come out of the buffer. Let's change the memory and the info. That looks good to me, and that should be everything except the calls themselves. Yes, it does look like that is the case. All right, so now we are not going to get rid of our global variables entirely just yet. Maybe we will later, but what I'm going to do is I am going to actually just declare now a global version of this thing, just to go ahead and quickly replace those places where we call it, and then we'll think about whether we want to replace it. We're going to call this the back buffer, the global back buffer for now, let's say, because we are only going to have one of them, so it doesn't seem like a particularly important thing to actually have that be local to anyone. Let's take a look here. Okay, I don't remember what order I even said that those things were in. Oops, didn't mean to actually create a new file there. Not my intention. Sometimes the Emacs keyboard shortcuts get away from you. It is totally true. All right, so this is the new function prototype that I made. We've got the device context, we've got the client rect, we have got the buffer now, this is global back buffer, We have got the parameters that used to be there, and that is everything. And the last one was render weird gradient. That just had to take the global back buffer as well. So let's take a look at that and just make sure that everything is copacetic with our code. Oops, change the name of that. Display buffer window. Good to go. All right, so now here is the part where we see whether I was correct about the fact that the capture in OBS should be working correctly now. If I hit F5, let's see how we do. Oh, my goodness, that is not a good situation at all. Well, that is definitely good. This is our first access violation. One of the things I did when I pulled that off was obviously a complete mistake. Probably something that was pretty simple. But instead of going and fixing it right now, I just want to talk a little bit about what just happened. In fact, let's run the code again so you can see it. All right, so whenever, you remember when I talked about virtual memory, when I talked about virtual address spaces, I said that by default, we do not actually have any pages in our virtual memory space, reserved or committed. And so basically what happens is if we go touch some memory, if we have a pointer, basically, that we try to write to, and that pointer points to an invalid page, then we know that the operating system will basically get that exception. It will basically cause the CPU to go, hey, wait a minute, that page is not something I understand. It should not actually be touched by anyone. So it'll go ahead and raise a flag to the operating system. The operating system will go, oops, and it will say, hey, you are touching invalid memory. You are trying to write, in this case, write, it could be read as well. You're trying to write to a page that I have not actually put in physical memory and that I do not think is supposed to actually be ready for writing. Now, it could be, when those exceptions are raised, that they're totally normal. It could be, like, remember I was saying you can basically reserve memory and then it will only actually get committed to physical memory when you actually need to use it. So it could be that the operating system wakes up and goes, oh, he is supposed to be able to write to that memory, so I'm going to go ahead and actually back it into physical memory now, and that's going to be good. But that is not what happened in this case. So we got what's called a segmentation fault on Linux sometimes. SIG-SEG-V you'll see sometimes. Signal segmentation violation, basically. Or on Windows, it's called an unhandled access, a UAE. I don't actually know what they call them sometimes in Windows, but anyway, it'll give you basically something that looks like this, where it says access violation, writing location, and then this is the pointer that you tried to write to. Now, if you notice, this pointer is awfully suspicious. It's all zeros. And basically what that means is we were trying to write to a pointer that we never initialized. So I probably just messed something up real quickly when I was changing the code to be using the buffer. And so we can go in and see. Now, it's pretty obvious what happened here. We're in the pixel. If the pixel pointer was 0, well, that means that our buffer pointer was probably 0, because there's no other way that could happen. So let's take a look and see. Yes, the memory is set to 0, 0, 0. So what happened there? Why did we not initialize that the way we thought that we did? So let's take a look. We come in here to Win32, resize div section. Here we are back out. This is in the WM size call. It's passing a pointer to the global back buffer, which at this point should have absolutely nothing in it. It should be completely uninitialized. And it is. So let's go ahead and step into this code. We're going to virtual free, but we didn't have to because the memory was empty. We're going to set our header. That's all the stuff that we actually wanted to do. That's all perfectly good. We're going to try and allocate memory here. The bitmap memory size. Oh! Well, there it is, ladies and gentlemen. There is the problem right there. That bytes per pixel. Huh, awesome. Well, I hope you guys caught that. That was a pretty simple mistake. But just to be completely clear about what happens, remember I had bytes per pixel in here, and I moved it out, and I did not actually set it to anything. So that's our problem. We got to set bytes per pixel equals 4 there. This would probably be a good time, too, to talk a little bit about assertions. I'd want to put them off a little bit till later, but so I have not been putting them in the code at all. Assertions are things that probably would have caught that error for us. But at the end of the day, one of the things you have to remember is it's not that important to catch all errors. Basically, that is an error that will manifest itself very cleanly. If we have an allocation failure, we will immediately have an access violation. So those are not the kinds of errors that we really need to guard against that much. Basically, there's two kinds of errors. There are errors that are very insidious and difficult to find. There are errors that don't manifest themselves very often. And there are ones that'll happen every time you run the program. If you have an error that happens every time you run the program, that is not an error you have to be worried about at all. You do not have to worry about preventing that kind of an error because you will always find it before you ship. The kind of error that you do have to worry about is the kind of error that does not happen on every run through the program so that you may not find it until you ship, and that is bad news. And so this is probably not the kind that you should be too concerned about, but even so, that is the kind of thing that if I was putting assertions in this code, probably would have found it. And so that is something that we will probably cover. It is 8:30 right now, and there's more stuff I want to do, so we're going to leave assertions until about 2 or 3 weeks from now. So I will not quite do that yet. Point being, that was the problem. If you didn't catch it, what happened is we used to have bytes per pixel in here set to 4, and then I changed it to being in the buffer, but I neglected to initialize it to 4. That was just a stupid thing to do on my part. And so what ended up happening is when we went in here to compute the size of the bitmap, well, we multiplied the width times the height and got the number of pixels that we needed, and then we wanted to see how much memory we need for all those pixels. We multiplied it by 0. And guess what? You don't need any memory to store pixels that have no size. So it ended up generating a 0, which passed 0 to virtual alloc, and when you pass 0 to virtual alloc, it passes you 0 right back because, hey, it does not have to reserve any pages to store nothing. Not a surprise. So, we should be back in good working order unless I made another stupid mistake. Let's go ahead and double check that. Excuse me, again, I apologize. Hopefully all my sore throat will be gone by next week. That is a much better looking size. We are in much better shape now. I think we should be good to go. So I'm going to go ahead and remove that breakpoint. And there is our beautiful pattern. Now you will notice how silky smooth that is tonight. Hopefully it's silky smooth on the stream. It's silky smooth for me. And again, that is thanks to Kurt. Thank you for writing in. We would have been in dire straits without you, my friend. Okay, so now that that is working, that is basically a very, very simple thing that you can do that I have shown, which is basically just taking something that was a bunch of global variables, pulling them into a structure, and now you have code that operates on that structure, which means you can have as many of those as you want to, and you also have a much easier time reading things because everything that you need is in one place. So that's always a good thing. Now, if we want to take this one step further, we could even get rid of this global variable. There really isn't much reason to do that because even though it makes it a little bit cleaner sometimes to do stuff like that, you don't want to go crazy and start doing things that you don't really need to do, because doing things that you makes the code cleaner in some conceptual sense, but that don't actually have any real payoff for you is just making busy work. And that is a bad idea. There's a lot of that goes on in programming. A lot of people who do things because conceptually they believe something is cleaner, but really at the end of the day, it's just what produces good, bug-free code in the least possible amount of programmer time. That is what you're looking to do. Oh, and it should be performant, obviously. That goes without saying. So if you are doing something that is strictly for some kind of conceptual cleanliness, you are actually doing something wrong. Because if that cleanliness does not pay off for you, if it's purely conceptual and not practical, that is a waste of time. And time is of the essence, especially here on the stream, because we only get an hour a night, ladies and gentlemen. All right. Where to now? What I would like to do, I think this program is relatively good so far. I don't have a lot of complaints about it, to be honest with you. But there's one more thing I wanted to pull out, and that is that we do this get client rect thing a lot. I was thinking maybe I would go in here and do something that basically made this a little bit easier for us. So I'm going to go ahead and make a little helper function. It's very simple. It is just going to be called Win32 window dimensions. That's all it's going to do. It's going to return a width and a height, just a very simple pair. And you will notice the reason that I'm doing that is you see this in a number of places. Get client rect, and then it has to do stuff with the width and height, that sort of thing right there. So what I'd like to do is just get rid of that redundant code a little bit because it's kind of looking a little ugly and I don't love it. I don't love doing the same thing multiple times like that. So I am just going to make a very simple call just for my own sanity and convenience that is called get window dimension, and it'll take that window handle and give that back to us. So there it is. That is the entirety of what we actually wanted to do. So I'm just going to declare one of these. This is going to be the result. And it is just going to, instead of creating local variables width and height, it's going to write that result, and then it is going to return it. That is it. That is all I wanted to do. And so now I can go down to the places that we did get client rect. And instead of doing that, I can do Win32 window dimension. I can ask for the dimension, get window dimension, and I can pass that window. Now that will clean up nicely. And here we can just go ahead and pass those dimensions to our resize call. That looks good to me. We can come down here to the same thing that was happening and actually do the exact same thing. And I'm going to change this display buffer in window call because instead of taking a client rect, I would prefer that it actually took the window dimension because that is what it actually needed. So I'm going to actually pass the window width and the window height here so that it doesn't have to deal with those rect structures, and that makes that code go through the exact same path as the previous code, which is always good. It's always good to have the less code paths, the better if you can avoid having multiple ways of doing the same thing for no reason. It just means it's easier to change later and more likely to find bugs because if there's bugs in each individual place that you do something, well, if you find and fix one, now you got to go and remember to find and fix all the others. All right, so what I basically did there is I said that when we were going to blip to the screen, instead of taking that client rect, it's going to take a window width and a window height. And you can see that all that had happened there is actually I had moved that window width and height computation that used to happen into here, so that's going to go away as well. So now we have it all done in exactly one place. That is pretty awesome. I love it when code comes together like that. You really can't argue with it. Of course, this is child's play with training wheels here. Obviously, we're just cleaning up some really simple code, so I wouldn't get too excited about it necessarily, but honestly, you know, what can I say? If it makes you happy, it makes you happy. You know what? I forgot to prefix that thing. Why do I keep hitting that hotkey? That is a hotkey that I should not be hitting. Okay, what I wanted to do is just add that Win32 there, because I was kind of following that convention, and I'd like to do that just so we know that things that are in our Win32 platform layer have a Win32 in the front of them. Just makes it a little nicer, makes it a little easier for me to see. So we are going to go ahead and get the window dimension here of that window. We are going to go ahead and delete this, and then we can pass the dimension like that. There we go. Okay. Yeah. Okay, well, you know what? I called it full dimension there. Let's be consistent for consistence sake. It is the goblin of small minds, they say. But you know what? Maybe our mind is small tonight. You know what? That could just be the case. All right, we are done with that. If I just can clean up the final... Oh, that's great, Casey. Nice. Gotta love the typos. Okay, and here we go. Dimension width and dimension dot height. Okay, now you may ask, while I'm cleaning that up, why do I keep passing dimension width and height instead of just passing the dimension itself? And the reason is because one thing that you want to make sure that you do is you don't go overboard with your type wrapping. So, the reason that I created that structure, the reason I created this structure right here is because I can't return two values from a C function. You can only return one. And so when I want to return two, I go ahead and make a structure that bundles those two together. That's why this is here. Otherwise, I just return two integers. And there's languages that support that kind of thing. And if you're using one of those, that is what you should do. There's no need to actually name this. It is not important. But when I actually start passing things, if I was to go down here and let's say change this to taking a dimension or change this to taking a dimension, what I have basically done is I have forced everyone who is ever going to call these functions in the future to bundle those things together again. They are now forced to create one of those structures in order to call my function, even if they already had the width and height from something else. And that is not something that I want to do, because basically when I make a function, I want the most number of people to be able to call it in the most number of circumstances, because that is what gives me leverage, and that is what allows me to reuse code the most often. So you don't want to get carried away with wrapping up your types. The only time you really want to force people to pass types to something is when those types literally have to all go together. Now, for example, in this off-screen buffer, that is a good case, making a good case for that, because all of these things are related. The pitch, the height, the width, the bytes per pixel, the memory, and the info all go together, and they cannot be used separately because they're all interdependent. Basically, this memory has to be a size that's dependent on the width and the pitch and the height and the bytes per pixel, and this info is set up to be specifically this layout. You cannot arbitrarily combine these things together. But Win32 window dimension is just an arbitrary width and a height that could have come from anywhere. It could have been from any window. You may have gotten it, not from calling this. And so I don't want to force people to pack things into some structure just to do it. So I didn't. Let's double check to make sure that we have not introduced any heinous errors by typos. We have not. That looks pretty good. Our resize is still working, so that's good as well. And that is all good. Now, I think that probably at this point, what I would like to do is go ahead and see, you know what, I might make one more thing before we drill down in the QA a little bit, because we've got about 17 minutes left. So there is one more thing that I think I'd like to try. Maybe this is a bad idea at this point in the stream, but I'm going to try it anyway. What I would like to do is I would like to start using our stretch split call to actually stretch our bitmap. I want to basically allocate this bitmap. Instead of allocating it in the WM size command, I'm going to stop doing that entirely. I'm just going to go ahead and say we're not doing that anymore. Instead, we are going to resize our bitmap right here. We're basically just going to go ahead and say that when we start up, we are going to make our bitmap a particular size. We are going to make our bitmap, let's say 1280 by 720. That is going to be the size of our back buffer. That is the way that I want that to work. And so now, when we go in and we do resize div section, we will do that just once. We will not do it on the WM size, and that back buffer will just sit around and get updated by us. Now, when we actually call win32 display buffer in window, that will stretch it for us, because remember, we're passing the buffer width and height, which will now always be the same. They won't be changing, but we will be passing a different window width and a different window height. So if we go in here and run this, you will now see that basically as we stretch, oh, that does not look good at all. Well, when I said you will now see a bug is what you will see. So that means we are passing some incorrect things here. What did we do wrong? Oh, that's fantastic. I just assume I know what the bug is here, because I feel like we typed the wrong things in there. Even though we read the manual, ladies and gentlemen, we've read the manual, but we must have ignored it, because I am pretty sure those are in the wrong order. Let's take a look. It is the destination first. Well, guess what, people? That is not the destination. The buffer is our source. The window is the destination. Those are in the wrong order. That is no good. That has been a bug that's been lurking in there. Before, they were both the same, so it did not matter, and that is true. But now we have fixed it, and there we go. So there we are. We're stretching. And that's totally fine. That's what we wanted to have happen. But I would point out that that is not a particularly good stretch, ladies and gentlemen. That is not a fantastic stretch. It is certainly not doing a lot of filtering to help us out there. So that's something to be a little bit concerned about, something to think about. So we'll have to play with that a little bit. For the time being, though, that means we do have a back buffer that's sized the same, and that is something that I want to start out with. And we will have to think about how we're going to deal with some of those things, because stretch DI bits may not be enough. May not be industrial strength enough for us. But we'll think about that as we go. It's totally fine for now. So one other thing that's going to happen here is if we stretch in some kind of way that actually does something bad there, right? We're stretching like this, we're stretching like that. We end up basically distorting the aspect ratio of our image, right? We are drastically changing the aspect ratio. So if this was our little handmade hero, he would be squashed. He would be squashed horizontally, or he would be squashed vertically. So what I want to do here is I want to just take a second to go ahead and actually correct the aspect ratio when we do this split. Because I wanted to show you a little bit of math for that. It's very simple math, nothing really too much. So basically what we're going to do here is we're going to try and figure out basically how... all right, I got to think about this carefully. 15 minutes left. These are the kind of decisions that are hard to make. You know what? No, we're going to save the aspect ratio for later. The reason we're going to save the aspect ratio for later is because it's probably true that we will want to do this in floating point. Maybe not. Maybe we want to do it in integer. I don't know. It's such a tough decision. Sometimes the decisions I face on the stream, it's the clock that makes the decisions difficult. I don't always know whether we should go for it or not. Well, the answer is no. We're not going to go for it. So I'm just going to drop a to-do in there. I'm going to say aspect ratio correction, and we will have a thing where we actually make sure we do that early in the stream so we can take the time to talk about how we're going to do it and do it 100% correctly. So for now, we're going to get a squash, and that is totally fine. But otherwise, we are totally good to go. All right. So last thing I wanted to do before the Q&A is we are going to go ahead and step through our code and make sure we understand what all of it does, so that everyone who followed us for this week can make sure that they really solidify their understanding of how the code goes. So let's go ahead down here and let's just set a breakpoint. Again, that's F9, ladies and gentlemen. Let's set a breakpoint right at the beginning. This is the first time that it enters our code. Now remember, we are not the first thing that happened. The C runtime library has already done a bunch of stuff, but there's not much we can do about that at the moment. There are ways to compile without it, but I don't know if we necessarily want to go there. We may try it at some point when we are feeling brave. Anyway, we go through here, and we are basically going to start by putting this window class, initializing it to 0. That, again, is going to initialize the window class to 0, basically because we have not put anything in the little brackets. That is the clue to the compiler to initialize it to 0. And where is that going to go? Well, where does any of this stuff go? All of this stuff goes on the stack. All this stuff goes on the stack. These parameters go on the stack. The window class went on the stack. And just to reinforce that, let's go ahead and take a look at that memory window, shall we? Here is the memory window. This is the memory in the computer. And actually, you know what I think I want that in a different place. I'm going to go ahead and just drag the memory window, and I'm going to go ahead and drag it down here so that it ends up down in here. That is not what I wanted. Ladies and gentlemen, I need to be a little more precise with my drop. There we go. Okay, that is the memory window. That is what I wanted. I'm going to go to the watch window, and I'm going to take the address of that window class, and so I can see where it is. So I'm going to take that address. There is the address right there. You can see it. It is a 64-bit address because we're in 64-bit mode, so we have big memory space. I'm going to go ahead and paste that in here and hit return. So this is where that window class is. You can see it. And it is not all zeros right now. It has got stuff in it, right? And I'm going to go ahead and hit F5 to step over, hit F10 to step over this line, and you can see that it all got cleared to 0 down there, right? So that is what's happening. This is the stack right here. And I just wanted to point out that if you look at where that is, 2CF5F0, right? 2CF5F0, where did you go? Right there. Let's take a look at those parameters. Instance, prev instance, and command line, just so we can see where they live as well. There you go. You can see that they are all right next to each other, which is what we would have expected because it looks like the compiler has pushed them onto the stack. It pushed them on the stack sequentially. We can see what order it put them on in the stack as well, right? You can see they go in order here, 30, 38, 40, and 48. And if we go ahead and look at where that is, we can see they are at 2CF7. They are a little bit further down. I will widen this out. So basically here is the one that we were talking about before, 5F0. It is right there. That is that one. And the 7s were over here, if I remember correctly. Yes, they were. Okay. And so what that leads me to believe, although I do not actually know, that would suggest that it is pushing these, that the stack is growing downwards. I don't actually know if that's true. That may not be true. It seems odd that it would push them in that order, so I'm not sure what order this stack is growing in. So let's go ahead and see if we can figure that out. Let's jump up the call stack one. I just want to know whether the stack's going up or down, because honestly, it's been so long since I've looked at anything like that. I have no idea on x64, which is what we're doing now. I have no idea if the stack gets bigger off the bottom of the stack or off the top of the stack. Let's find out. All right, so see, here's a variable, init_ret. Let's see where that is. Oh, it was optimized away. All right, well, all right, so much for that. Let's call into one of our functions then and see where it is. So let's go down here real quick. Actually, you know what? No, we can do, why did I do that? We can actually do that right here now that we're allocating our back buffer. All right, let's take a look. Window class. That is where window class was placed on the stack. That is this location in memory, 1FFCA0. And all I want to know is whether the stack grows downward or upward, meaning when you push new things on the stack, do they go at higher addresses or do they go at lower addresses? That's all I wanted to know. Just wanted to get that out in the open. So let's take a look at where some of this stuff goes. So here we are, bitmap memory size. That is a local variable. It should be on the stack here. Let's see where it is. And so 1FFCA0, and we have 1FFBF0. That looks a lot to me like we are growing downwards, ladies and gentlemen. Let's just verify that that's true. That does not necessarily surprise me, but I just want to make sure that that is true. Oops, that is the wrong way to go. So this is the value that is lower. This is the one that's further down in the function, basically in the depth of the function. This was the one, bitmap memory size. And so this was a function that we called the deepest nested function. And here's the one from the function that called it. Hit return, it is 176. Yes, so our stack is growing downwards. What that means is that every time something new is pushed on the stack, it goes at lower and lower memory addresses, which is a little odd because normally you think of things as growing and getting higher and higher, but it looks like the stack is growing downwards. Just something that's good to know. Does not really affect anything in any particular way, but just something interesting to think about. Also, I guess that means, and those of you who are hardcore assembly guys, correct me if I'm wrong on this. I don't want to speak out of turn, but I guess that means that if this is the value that the stack is at now, that's the entirety of the stack size we actually get. So basically, we can only add about 2 megabytes to the stack before we would get to the null page at best. So it can't be any more than that. Our stack must be less than 2 megabytes. I don't know if that's actually true, but that's what that would seem to suggest to me. Do you understand that? Do you guys understand that at all? Basically, what I'm saying is, if I've got a local variable in this function right here, and I say, where is that? Right? I say, where is it? It tells me it's right here. Well, that's where in memory the stack is at. And every time we go ahead and push things on the stack is usually contiguous rather. It does not use disparate addresses in memory. It uses contiguous addresses in memory. If we are subtracting from the stack every time, if those numbers are getting lower, then that number certainly can't go any lower than 0 because we know that 0 is a null pointer and that would cause an access violation, and that whole page would be an access violation, at least 4096. So somewhere down there is access violation territory, which means that this pointer basically represents the maximum amount of stuff we could push on the stack. That value is the maximum number of stuff that we could push on the stack. I hope that makes some sense to people and I'm not just rambling, but that basically means to me that says, you know, if you go ahead here and said, well, that divided by 1024, that is kilobytes, and if I went ahead and did 1024 times 1024, now I'm just looking at how many megabytes, and it's only 1 megabyte. It's a little more like, it's almost 2 megabytes basically. If I actually did this in floating point math, I'd see a little bit more. But that is kind of scary. All right, so you have a 2 megabyte stack to work with. I guess that's just how much you get by default. Now, there are things that control how big the stack is, certainly. You can change the stack size if you think you need more than that, but that's just something to understand, that basically, as you are calling functions, when you call functions, if you were to put gigantic things on here, you might run into a problem. Just because we are being kind of strange tonight, I guess we could sort of see how big that default stack size actually is. Let's go ahead and just be a little rascal, just be someone who's just screwing around for fun, because it is Friday, and that is our prerogative. Let's go ahead and see what happens at the 5-minute warning, no less. If we just told this thing to allocate a bunch of memory, big old block of memory right on the stack, I don't know how it will fare, but I'm going to go ahead and say, go ahead and allocate 2 megabytes right on the stack. What do you think about that, Mr. Compiler? What are you going to do? Well, it worked fine, so I don't know what happened there. This is a little puzzling. This must be one of those things where I'm going to look at the stream afterwards and you guys are going to say, you're an idiot. And that may be true, ladies and gentlemen. I may well be an idiot. So let's take a look at big old block of memory and where that points to. There we go. It is oops. What did I do? It is undefined. Oh, well, the optimizer optimized it out. I guess. I didn't think we were compiling in optimized mode, so I'm surprised at that. Is that really true? Well, see if we go ahead and clear that, maybe. Let's see what happens if we clear that. And then maybe we'll do something ridiculous. Since the optimizer's not on, is that going to work? I don't know what's going to work. I don't know how we're going to get it to do that, ladies and gentlemen. Let's take a look. There it is. That's what I was looking for. Stack Overflow. Thank you, ladies and gentlemen. We have done exactly what we tried to do. That is great. That is what I was hoping for. Now that it has not been optimized out, maybe I just didn't recompile. Maybe that's what happened. I don't really know. Point being, basically what I did is I forced the compiler to make a 2 megabyte thing on the stack, and since I noticed that particular time through the program, it had given us an address that was less than 2 megabytes away from the bottom of memory, I figured that the default stack size couldn't be any more than that. Now remember, in Windows for security concerns, our stack will be at randomized locations. So it will not always be there, but just noticing that, I figured, well, that means that if it has to allocate stack for us to run, it could not have been trying, there's obviously no way that the default stack size could have been any bigger than that, because it obviously thought it was okay to give us the memory down that low. So what I did is I just made something 2 megabytes large to see whether it would just roll over and die. And the answer is it did. Now you can take a look at that error. It basically is the same kind of thing we got when we were writing to invalid memory, but this time instead of access violation, it is a stack overflow. And that is exactly what we did. We overflowed the stack, we asked it to put too much stuff on there, and we got this error. And that was what I was hoping to show you, because I just wanted to underscore the point that memory is not free. It does not come from some sort of little magical memory pixie dust fairy who sprinkles it on us and gives us as much as we need. That is not what happens. Even the stack, which is managed for us automatically by the compiler and by Windows in some sense, does not actually give us carte blanche. We still have to be totally aware of how much of it we have, and every time we call a function, we have to know how much stack space we're using so that we do not get too out of control. Now, we should never really be using something that's going to allocate 2 megs of stack space, but you may be surprised if you were to do something that's called a recursive function, which is a function that calls itself and uses the stack as temporary memory, something that we might do in the future just to illustrate the point. You can easily get into a situation where maybe you call yourself 40 times and all of a sudden each one of those things, if it's just using maybe 50K of memory, let's say, on the stack, which is still a huge amount, or maybe 10K of memory, that adds up to half a megabyte right there, and that's a pretty big stack commitment when you know it's less than 2 megabytes. I guess one thing we could do is we could be a little bit more investigative here and just start, instead of just looking, we could always just go look up how big the stack is, right? But what fun is that? Why not just go ahead and figure out how big it is by trial and error, right? Okay, so we're down to let's go to a half a megabyte. Let's see how that does. Half a megabyte worked just fine. So maybe we'll go up a little bit higher. I don't know what to do here. Maybe something like that. Let's see how that does. We are still okay. So I don't know how close we can get to 1 megabyte of stack in our first function before we cause a problem. Looks like we can get real darn close to it, huh? Really darn close. So let's go a little bit closer, and still not stack overflowing yet. This is going to be interesting. It's going to be tight. Are you as excited as I am to find this out? Where are we at? Alrighty, we have stack overflowed. So we're real close, and when I say stack overflow, I mean the interesting kind, not the website that has weird answers to questions that are sometimes wrong. All right, there we go. We are almost there. We'll binary search this down A little bit closer. A little bit closer. That is real close right now. There we go. Okay, so we know we are basically at something like this. Something like this. We are really close. Something like 1,000. 1,000K. Okay. All right. So we know that it's somewhere between 999 and 1,000K. Oh, or maybe not. What's going on there? Unhandled exception during user callback. Wait a minute. Oh, ha 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 ha. That's pretty funny. So we have actually started stack faulting down somewhere else because we gave just enough stack for us to exist. But as soon as we start calling down into Windows, we forced Windows to fault. That is excellent. That is excellent. So we know, we have something like a megabyte of stack. That was kind of fun. We know we have something like a megabyte of stack when we enter our first function. If we don't tell the compiler to give us more, I think there is a flag that basically tells the compiler to give us more. If we were to go in here and look at that, we could search for stack, and we would probably find something. Let's see. Force parameters, set stack size /fnum, and I assume that basically if we did a /f, we could have our cake and eat it too. Remember, we cannot make something this big. We tried to make something that big. It was 2 megabytes. Let's go ahead and run that, and that totally faulted. So now let's ask for a giant stack, ladies and gentlemen. Let us just see what we can get away with. Let's do 1024, 4 times 10. What is going on? That is no good. I'm in the wrong mode altogether. There we go, 4 times 1024 times 1024. We will just copy that value. We'll get a nice 4 megabyte stack, in theory. We'll go back in here, and we'll go to the build.bat, and we will do what this thing said to do. Where was that again? Sorry, it was F. Where was that? Where are you, Mr. F? Fnum. So just /f and then that value. Okay, let's do that. -f and that value. And let's see if that gives us a bigger stack. Look at that. We can have all the stack size we want, ladies and gentlemen. That is a very generous stack indeed. Hopefully we will not need anything like that, so I'm going to go ahead and delete that. But just for the sake of completeness, I wanted to show you that we had control over it. All right, I'm going to go into the Q&A a little bit today, just because I wanted to step through these things. And this is basically an entire day, essentially, of Q&A. Maybe we'll let the Q&A run a little bit long if we have to. All right, here we are. We basically clear these things on the stack. We are going to go ahead and initialize our global buffer, back buffer. So we're going to call back in here. We're going to pass it a pointer. Now, where is this thing? Where is this global buffer? Well, that's basically something that was created at the initialization of the program. So that's just memory that's not on the stack. That's memory that's permanent. We do not have to worry about it. And you can see that's in a totally different location. Nowhere near the stack, right? If you look at where the window class is, that's very low. And if we look at where this back buffer is, that's very high in memory by comparison. So they're nowhere near each other, and that is kind of what you'd expect because this is not on the stack. This is data memory of our program, static data memory that was basically created when we launched the executable. Said that we basically said we needed that memory to run. All of our global variables go into it. All right. So we go into resize div section. We are going to allow this call to be called as many times as we want to. So what we do first is we check to see whether we already allocated memory for our buffer. And if we did, we will get rid of it. If we didn't, we basically just fill out a bunch of fields that we will need to remember, the width and the height and the bits per pixel, bytes per pixel, which is things we want to know. And then we are going to go ahead and fill out that information that Windows needed basically to do the blit later on. And you'll notice we have to pass that later on. So that's basically a description to Windows that says we are going to pass you a bunch of memory and here is how you interpret it. Now remember, we had this negative here. In fact, you know what? I'm going to go ahead and add a comment to that because it's a little confusing to people who don't know what's going on. I'm just going to add a comment there that basically says, note, when the BI height field is negative, this is the clue to Windows to treat this bitmap as top-down, not bottom-up, meaning that the first byte of the image is the top left. I guess I should say the first 3 bytes of the image are the color for the top left pixel in the bitmap, not the bottom left, right? Make sense? Okay, so that is all that is, and I just wanted to get that out there. All right, recompile that. I haven't really changed any code. So we come back down in here. We basically compute how big we need, because we're going to ask for a permanent chunk of memory. And you may ask, well, why didn't we just do what we did up here? Why don't we just declare the chunk of memory up here? And we could have done that. That is totally valid. The reason I didn't want to do that is because I wanted to make the size of this bitmap be parametric, meaning we could change it at any time in the code. And if we had put it up here, it would have to be known at compile time. We could not change it. We could still do it up there by just doing one that was so big that we knew it was always as big as the biggest one we could possibly ever need. We could totally do that, and maybe we will do that eventually, but for now, I wanted to show you how to use virtualalloc as well. So we went ahead and did virtualalloc, which of course asked the operating system to reserve memory pages for us. It asked us to reserve this many. Basically, however many memory pages it needs to take this much, to hold this much data, to hold this many bytes. And the thing that you have to remember is this will allocate in increments of the page size. The page size, I believe, on Windows is normally 4096 if you are not using large pages, in which case it is 64K. And what that means is we probably will not use exactly the right amount of memory here. We will get back more memory than we needed, just a little bit more than we needed. So if you look here, this is the actual size we're asking for. If I am to go ahead and divide that by 4096 and then multiply it back by 4096, let's see what we get there. Well, that looks like it actually, let's optimize that out. Looks like we are actually right on a page boundary, if that is actually true. Let's double check that just to make sure it's not doing something fancy thing here. So, excuse me. Apologize again for the cold. Okay, this is the size we had. This is the page size that I believe Windows is using. There's a way to get that page size, and we could do that a little bit later too. Maybe we'll do that right now. If that's the page size, then we know we are asking for at least 900 pages, possibly more, and I just wanted to see if 900 pages basically times the page size comes out exact, and it turns out it does. So it turns out we are asking for exactly an even number of page sizes, so we are not wasting any memory, ladies and gentlemen. How about that? Totally accidental. Normally what happens with virtualalloc is you will waste a little bit of memory at the end of it, and so the thing that you typically use virtualalloc for is not to allocate little chunks of memory. You use virtualalloc to get a bunch of memory that you then subdivide, and that is exactly what we'll be doing with it, but right now we only have one allocation in our entire program, so there's really no way we can do anything more optimal there, so we just go ahead and call it. Anyway, we store the bytes per pixel back here, and when we multiply the width times the bytes per pixel to basically get the pitch or the stride, depending on what you want to call that. And basically what that is how many bytes a pointer has to move to go from one row to the next row. And of course, that is the width, the number of pixels across that the bitmap is, times the bytes per pixel, because we need to remember that each pixel itself is actually 4 bytes. Since each pixel is 4 bytes, that means that we could not just go width number of bytes, we have to go width times 4 number of bytes because we have to skip the R, the G, the B, and the pad for each individual one. All right, so when we finish, we then fill out our window class. Remember, a window class is just something we register with Windows that tells it where to call back when a window needs to actually field a message. We fill out an instance because Windows needs to know who to call as well. So if you imagine, basically when I talked about the fact that we have a virtual memory address space for our program, right? Well, that virtual memory address space contains our code as well. So if you want to call us back, you have to know which virtual address space you are calling back, right? Windows needs to know which process is actually holding the function, because if I just say, here is the address of a function, well, that address is in my process's virtual memory space. If you didn't know which process you were calling back, you wouldn't know what that address actually refers to, because every address space for every process is different. So a pointer does not uniquely identify memory in the system. It uniquely identifies memory in one process. And so without the process handle, Windows would have no idea who it was even calling. So basically what this is that handle. This is the instance that says this is the actual process that contains this pointer's memory. So interpret this pointer in its address space. And then it can do the dispatch. We give our window class a completely meaningless name because we need to do that, because we are going to pass that name to create window EX, so it knows what window class our window is using. Of course, we only have one, so it's a real waste of time, but that's just something you have to do. We register the class with Windows by passing a pointer to this stack variable that we have here. Now, we don't have to worry about that ever going out of scope because we won't exit this function, but we don't have to worry about it going out of scope, period, because Windows will actually snap a copy of it. It does not rely on our copy, so we don't have to make sure that that copy stays around for as long as we use anything. It is just going to use it to read the memory out, and then it is going to return. and we don't have to worry about keeping it around anymore. You need to remember that sometimes you do. Sometimes when you pass an address into Windows, you have to make sure that the thing you pass the address to stays around for the lifetime of the things that might use it. This is not that case, so you don't have to worry about it here. We then go ahead and do create window EX, and basically all we do is pass the window class that we wanted, and that's so that our window knows, so that Windows knows that our window is going to call this callback anytime it gets an event. We told it that we want it to be visible right away so that it shows up on startup, and that it was a WS overlapped window, which is basically just a composite set of flags, a composite set of bits in this bit field. This is just a 32-bit value that's got a bunch of bits set that Windows will look at each individual bit to determine a bunch of things about the window. It is basically just a composite that says it has things like a title bar and a close box and things like that, a resizable frame. And we also pass the instance of this as well because, again, Windows wants to know what instance is calling it. I think those are probably somewhat anachronistic these days. I don't actually know if you actually really need to pass those to, I mean, I think you do need to pass them or Windows will be upset with you, but I don't know how much they need because they know which instance is actually calling it, so I'm not sure how important that is. I think those may be somewhat anachronistic, but ignore that for now. We create our window is created. Assuming that we got back a handle that was valid, we assume that we are ready to run. We go ahead and enter a loop that is infinite. It will not exit until running is set to false by someone else in the program. Running, again, is a global variable, and maybe one of the things I will do is change that to have a prefix global, just so everyone knows it's global. I don't often prefix things, but for globals I often will change that rule just because I think it's important to be able to see when something's global, so that's a good habit to get into, I think. Something that's worth thinking about if you are thinking about code styles. Something that's not bad to do. Yes. So anyway, we go ahead and enter our loop. We create some space on the stack for Windows to store its message because it needs a place to write it. We call peek message, and again, what peek message will do is it will look at our Windows window queue. For our process, it will see if there are any messages in there for us, and if there are, because we passed PM remove, it will go ahead and give it back to us. Now, I passed all zeros here, which means it won't filter the messages. It will not do anything like only give us ones for a certain window or only give us ones that fall into a certain message range. It will then see whether or not, or rather we will then check whether or not it was a WM quit message, just in case Windows sent us one. Now, it should never send us one, I don't think, but just in case it did, we will go ahead and set running to false there. We will then ask Windows to translate message, and translate message again, something that just translates key codes. I don't actually know how much we actually really care about that, but it's something that you typically do. And then we dispatch message, which will again call our window class as necessary. Now remember, Windows can call our window callback anytime. It does not need to only do it in dispatch message. That's a little bit of a gotcha, you would think, but that is not the case. So we have to be ready, actually, anytime we call a Windows call, just keep in mind it could call you back. Now, after we loop through there and pull off all the messages that Windows has for us to pull off, we go ahead and call render weird gradient. And render weird gradient goes through, and it snaps a pointer to the beginning of our back buffer. It then steps through every row of that back buffer and grabs a pointer to the beginning of the row. Remember, we are advancing row each time. We advance it by pitch each time through this outer loop to get to the next row, because remember we said the pitch was the thing that moves us from one row to the next. We then grab an individual pixel pointer by basically saying, okay, let's take a look at row. Now remember, the pitch is in bytes. We said the pitch was going to be in bytes. How do we know the pitch is in bytes? Well, if we look at where we computed it, you'll notice that we multiplied it by bytes per pixel, right? So we are looking at a value that is in bytes. So when we add to the row had better be a pointer to bytes, which it is. Otherwise, C will do that silent multiplication for us, and we will add too much, ladies and gentlemen. If this were pointing to a uint32, we would actually move 4 times the amount we were supposed to move, and that would be bad. So that's why that's a uint8, very important there. We are then going to go by pixels here, so we cast to a uint32. Again, these are the same pointer now, we've just copied it in here, but then we're going to advance this pointer for each individual pixel. So we come in here, we go for each pixel in a row. We basically used a little faux value here to just say, hey, well, let's assign the x and y, just to give us a little bit of a gradient so that x increments here. And it will wrap, remember, this is a uint8, so it means that when the x value gets plus whatever the offset is that we passed in to make it animate, but that'll be 0 the first time through. These will both be 0, and they'll just kind of increment to make us get that animation. But basically, every time we overflow 8 bits, so every time we get to 255, when we add 1, we will go back to 0 because we've only got uint8 here. And that's what creates that 256 by 256 block pattern that you see in our gradient. It's those 8 bits wrapping, rolling over every time. We then go ahead and write that out to the pixel pointer. We use a nice little notation here, which is basically very concise. That is C shorthand. I'll just say it again because I think everyone should probably know it by now, but I've never really explained it on the stream, so we will make it clearer. Star pixel means I am trying to write to the location of pixel. That dereferences pixel. Basically says, okay, pixel is a pointer, but I now want to talk about the thing that's at that pointer, right? So if I put it on the left-hand side, I am writing to it. If I was to put it on the right-hand side, I am reading from it, in a sense. You could think of it that way. So if I was going to write to it, I could write to the pixel here, write some value into it. And so that is what the star does. The plus plus is the post-increment operator. It says after this line, after this statement, I should say, after this statement, I want you to increment this value by 1, right? I want you to increment it once. So basically, this is the same as saying star pixel equals something plus plus pixel, right? Or pixel equals pixel plus 1, right? Now, it's a little deceptive again because it is a uint32 pointer. So really what will happen here is the compiler will silently do that. So it'll really add 4 to it. But that is exactly what we want when it increments pixel, because each pixel is 4 bytes long. So that is exactly what we want, and C is just saving us some time there. That is what it is doing. Now, in here, we need to pack our pixel, as we know. Inside our registers, we have a thing that looks like XX, RR, GG, BB in memory order. That is BB, GG, RR, XX. So in order to pack these into the register, we go ahead and do blue in the bottom bits because we know that that is the least significant byte. Then we pack green one above it. We don't have any red. We don't have any pad to write, so those stay 0. That produces our new pixel value. And when the CPU, remember again, that's in there. It's in our register looking like XX, RRGG, BB, right? When that goes to be written out, since Intel is little endian, it will reverse the order. It will write the BB to the lowest one. It will write the GG to the next one. So that will basically do that reversal into memory to make the memory order go like this. First byte, second byte, third byte, fourth byte. Just something to remember. Okay, that is the little endian at work. This basically produces our gradient, that lovely thing on the screen that animates for us. And that is the way that works. Okay, that is the end of our helper functions. What is going on here? Why can I not unset that breakpoint? F9 is not behaving tonight, ladies and gentlemen. I do not know why. There it goes. Okay, that's good. Anyway, let's go ahead and recompile that now. There we go. One thing you should be aware of is that if you have a program stopped in the debugger, like this, and you go back and you try to compile something, it will say this: cannot open Win32 handmade.exe for writing, and that is because the debugger actually holds it open. So basically, well, it's not really that the debugger holds it open, it's that it's running, so Windows is kind of holding it open, you could think. That is the downside to Windows. It does not happen on Linux machines. Unix uses a different system. It's got inodes, and they get referenced, so you do not have to worry about that on Unix, but on Windows, you do. I'm assuming on Mac you don't either because it's Unix under the hood, but I don't actually know if that's true because I don't use Macintosh very often. But at least on Windows you do have to worry about it. So always make sure you hit Shift F5 to kill that debug before you come back here and hit Alt M to build if you are building an external editor. All right, so we come back in here, render our weird gradient. Oops, didn't mean to do that. There we go. Render our weird gradient. We get a handle to the window, which is basically just a way of us asking Windows, we're trying to do some drawing now. Can you please give us back a handle that allows us to issue draw calls? Purely artificial construct. Windows just wants to bound those because those save state. Basically, you can later on, well, not later on, probably. If you did your own investigation, you would see that you can do things with device context like draw lines and stuff like this, and you can select things into them like brushes and patterns and stuff. So they're a whole state tracking mechanism basically that we don't really need, but all drawing stuff has to go through it when we're on this path, so that's the case. We use the helper function that we called to basically get the width and height of a window. We did that by asking Windows to give us back a client rect, which is the writable region of a window in Windows space. So basically left and top are always 0, and right and bottom are always the actual width and height. But just in case they should change that someday, we actually went through and were a little more diligent and subtract the left and top. But pretty much always, every time you go through there, as far as I know, that is redundant. As you can see, the left and top is always 0, so that subtraction basically does nothing. The right and bottom is basically the width and the height, just right there. Okay, when we step out of that, we've got it. We ask Windows to display it by calling stretch_gi_bits, which is just a function which stretches our off-screen buffer up into or down into the Windows size. So we pass it the Windows size and we pass it our buffer size. We also pass it that bitmap description that it needed so it knows how to copy it. knows what it's looking at, and we pass it the memory. We also gave it some flags that told us how to do the copy. Nothing big there, just says it wasn't palletized, so it doesn't look up a color palette or anything like that. It's just their straight RGB values right in the pixels. And we passed it source copy, which tells it don't do any operations to the bits, just copy them. That's about it. All right, so we come back out here, we release the DC because this is a get and release mechanism. When we get one, we have to give it back. And so then we increment our gradient offset, which allows it to look like it is animating because we update it. And we will just come back through here, and this loop will happen ad infinitum, pull off the messages, re-render the gradient, pull off the messages, re-render the gradient, and that is our program. It will not stop until we get a window message, and the window message is the close message, at which point we will stop. So if we are running and we close that, we hit here. Now, that will set global running to false, break out of that loop down at the bottom of the program, because you can see that it only goes as long as global running is true, and it won't be true anymore, so it will exit. That is what that will do. Now, there is one other thing that our program does. We have this window callback, but besides just fielding the close message and the destroy message and so on, and some of these other ones, we can get rid of that one now. And this one we're going to handle a little bit later. Basically, we have this WM Paint in here. And what WM Paint is, remember, basically one of the things that we're doing is we are force painting the window to make it animate. So we're just flat out going, anytime we are done processing messages, as fast as we can using all available CPU resources, just blit. Process the message, blit. Process the message, we're just we're like a little, we're a chihuahua on speed here. We are just blitting and blitting and blitting and blitting and blitting and blitting. And that is fine. But Windows also sometimes will call us back, and the times it will call us back is when it suspends the running of our process. Basically, it blocks the running of our process to do a size. So basically, when we go into this, you'll notice we are no longer running. We are blocked in that message queue. Windows is not letting us continue. That is something that happens when you resize a window like that. And so while that is happening, Windows is actually telling us to repaint. And so we are actually fielding that message in here. And so if you look at what's going on here, we are just going ahead and we are asking it to do the same blit it was doing outside, but we're doing it inside the paint. Now, one thing that you might notice is this begin paint, end paint. That is basically something you need to do in the WM Paint message to tell Windows that you have updated the dirty region that it is asking you to repaint. Some people asked me about validate region or validate rect. They were reading the documentation and they said, don't I have to call validate rect so Windows knows I finished painting? And the answer is no, you don't. End paint automatically tells Windows that the paint that you asked it to do, that it asked you to do, was done. So that is really all you need, is that end paint. You don't have to do anything else. End paint implicitly will validate the region. And if you're wondering what validating regions are, you can go read the docs too, or I can give you the quick capsule summary. And that is basically that Windows remembers where on your window it needs to repaint. So basically, if you actually run the program here, if I run this, and I do something like move it off so that it gets obscured and then move it back on, Windows remembers that area that was obscured and calls you back with WM Paint asking you to paint that area. And it wants you to tell it at some point that you actually repainted it so that it knows it can stop asking you to repaint it. If you don't, it'll keep sending you WM Paint messages until you do. And that will flood your message queue with extraneous WM Paint messages, and you don't want that. So you always want to make sure you do something, either begin paint, end paint, or validate the rec yourself, but I would recommend doing it this way. This is the right way to do it, I think. Basically to make sure that Windows knows what happened. Now, anytime we got a message that we didn't handle, that's the default case of our switch statement, we just let Windows handle it for us by calling the default window procedure, which is basically just a catch-all. It's a thing defined by Windows. It just does the right thing by default for any message that we don't want to handle. And ladies and gentlemen, I think we have come to the end of our program. It was a good program. I've seen a lot of people email me who said they had a lot of fun playing around with this buffer, making weird patterns, doing all sorts of stuff like that. And I am absolutely delighted about that, because this is really the joy of programming right here. Once you can actually start poking right to the bits and seeing that happen, and you're basically, it's you and the CPU, and it's just, you're just having a ball. That is really some of the, that's programming being fun again. You don't have to worry about 800,000 libraries that you're using and they're not working, and linker errors, and try to go to Stack Overflow to find the compiler switch that makes it so it does. None of that. It's just a simple build file, and everything is under your control. And that is what I love. It makes programming fun again. It's like booting up an old Apple II and hitting that control break or whatever it was. Like, God, it's been so long I can't even remember, but you could go in there and just start typing in basic code and doing all kinds of weird stuff. It's that kind of fun again. All right, ladies and gentlemen, we have come to the end of Handmade Hero for the day, but I didn't want to take up all the Q&A time, So I am still going to do a bunch of Q&A. Maybe we'll go a little bit longer because I had to take a little extra time there just to essentially do Q&A, which is to go through and really try to solidify a bunch of stuff that people might be asking about. But you may still have some questions. So let's go ahead and go to the stream, the Twitch chat. Would it be a good or bad idea to get one device context at the beginning of the program and use that for every iteration of the main loop? So interestingly enough, that is not really allowed, I do not believe, by Windows usually, unless you ask for it specifically. And that is actually, ironically enough, specifically what this flag that I said we probably don't need does. And if we say CS own DC, basically that means that every window in this window class will get its own device context that it no longer needs to return. And so you could argue that maybe that is a good idea. I mean, you know, because why not? And then what we would do is we would just specify that own DC, and then I'm pretty sure that it's completely legal at that point to just say as soon as I get the window, I'm just going to snap the DC, and then I never have to give it back again, right? And I'm pretty sure that just works. I could be wrong about that. If someone at Microsoft right now is having an absolute conniption because I am telling people to do things that are going to make their life harder, I do apologize for that. But that is just my understanding of how the DC system works. Now, of course, there are other times when we use a device context, but I think they're pretty much only in the paint. And since Windows is already giving us back the device context it wants to use, I don't think that's a problem. So I think this would be totally fine. I'm going to go ahead and say, note, Casey, since we specified CS own DC, we can just get one device context and use it forever because we are not sharing it with anyone. Yeah. Let's see. Can we please add a Chihuahua on speed as a sidekick or enemy monster? Yes, we can. Chihuahua on speed will definitely be written down in the notes if that becomes. Why do you tell Windows you handle messages you don't really handle and default is good? And default is good. I don't know what the and default is good means. Well, so I can answer the first part of that, which is why do we tell Windows we handle messages which we don't really handle? And the answer to that is the concept of handling a message is a little bit fuzzy. What it means to handle a message is really whether or not you want Windows to do anything at all in response to that message. And so basically, you know, yeah, I can delete that WM size and nothing really is going to change in the program, right? It's going to be basically exactly the same. And so that's fine. The reason for that is that there really isn't anything by default that Windows needs to do in response to those messages. Now, to destroy and close, there are things it might do in response to those messages that are default, and I don't want it to do them, so I'm not letting it have a chance to do that. Activate app, same thing. I actually have stuff that I want to do there. Now, you can usually check inside the WM, the documentation for whatever the thing is that you want to see whether it recommends that you still call Windows even if you don't do it. If you don't do certain things, it'll say like you have to do these things in response to the message, but usually there isn't. Return value. If an application processes a message, it should return 0. So it doesn't. If the Windows message isn't documented as requiring certain things to occur, and there's nothing that we want to occur, then it is equivalent essentially to having a case or calling def window proc. There's no difference. But there are certain window messages in response to which you do have to do things. And so if we were going to field those messages and we did something like this, where we didn't actually do the things that were required, that would be bad. So really the only thing you're trying to avoid by having this default here is that for those Windows messages that require mandatory work on your part, you have to call them. Now, I can give you an example of one of those right off the bat because we already said it, WM Paint. if you don't do a begin paint end paint inside WM Paint, your dirty region will never get validated. That means Windows will continue to think it's dirty and it will flood you with WM Paint messages. So if we were going to do something like this, that would be bad. You don't want to do that. You would want to delete the case entirely and make sure that you're calling def window proc, because that will do basically a null paint right there for you, and make sure that it considers the region validated and there will be no further problems. Let's see. I believe set stretch blip mode will allow you to get better quality stretching. I believe you want halftone. Yes, I think there are some settings we can set. We will look at that a little later. What I really want is filtering. We may not get that, so we may write our own filtering code. But I will add a note in here, or to do, I should say, when we do that aspect ratio correction, we can play with stretch modes. Yeah. Let's see. Okay. Hi, Casey. Can you please explain pointer aliasing again? I didn't understand how passing by reference would cause a problem. And someone else asked, when you're talking about passing by value versus passing by reference, you mentioned there are modern optimizations. Okay, so let me handle these two. Stream has ended. Don't look at that, ladies and gentlemen. Do not look at the little thing that says stream has ended. We will go a little bit longer tonight because I was kind of in the mood to talk about stuff. So we'll go a little bit longer here on Friday. We'll all be up late at night partying anyway, I am sure, so there is no harm done. So what basically happens here, I'll try to give an example. And basically, I want you to take this example with a grain of salt because, like I said, I am not a compiler author. And because I am not a compiler author, my examples may be wrong in ways that are actually important. So what I would highly recommend you do is go watch some lectures by Chandler Careth. I believe his name is spelled Chandler Careth, like that. He's one of the guys who does optimizations on LLVM, which is a really, really good compiler compared to all the other compilers out there at the moment. I would go watch some lectures by him and watch him explain some stuff because it is true. I found out about him through Fabian at Rigorous. Him on Twitter. He's a friend of mine, works at Rad. Really, really awesome coder. I think I mentioned in the stream before, and he had been posting some links to some of his lectures like maybe a year ago or more. And basically, they're just really, really good, down to earth. Like, here's what happens in the optimizer when we're trying to optimize your code, so please understand these things. All right, so here's basically what happens. Aliasing. There are multiple kinds of aliasing. There's basically aliasing that happens. There's cache aliasing. I think there's TLB aliasing. There's all kinds of aliasing that happen. Most of them have to do with the CPU. And most of them have to do with optimization. So when you're talking about aliasing, you're usually talking about a CPU performance problem that occurs because you have had some unfortunate coincidences with the actual addresses where things are stored in memory. Okay? So when you see aliasing, that's usually what that means. But in this case, when we talk about aliasing, we're actually talking about something totally different. So I understand why it can be confusing because the word aliasing gets used in a lot of contexts, and those are not the contexts that we mean. What we're talking about is we're talking about very specifically pointer aliasing, which is a language problem. It has nothing to do with the CPU at all. It is completely unrelated to the CPU in this case. Although, I mean, you could talk about things that happen in the CPU that might be relevant to things, you know, that might have similar things like this. But we're actually talking about strictly during the compilation of your program pointer aliasing. So what that means is when you define a function, you need to think in terms of what the compiler actually sees. So let's say the compiler sees a function called do the stuff, right? And it is going to take a pointer that you call int star from, right? And it's going to take another one that you call int star 2. And now because you're one of these C++ fanatics who likes to put const everywhere in your code, you even tried your best to tell the compiler that from is const. It's constant. I'm not even going to talk about what const means really because I never use it. But let's say you even were somebody who is really, really into const. So you put const everywhere in your code. All right, so you've got this. You're saying I'm going to read a from, and then your code does some stuff. Now the example I gave, in fact it's called do the stuff, right? The example I gave was, let's say that we did something like, star star2 equals star from, right? Like this. That's what that does. Let's say I do that a few times, right? So I, add some values here to these pointers. I'm moving them around however I want to, that sort of stuff, whatever, dot, dot, dot. Stuff happens, right? So here's my function. So basically, what's going to happen here is when the compiler is actually generating code, and this is not really the best example. I really need one other thing here that's going to happen. You know what? This is better. This is better than that. There you go. So what's going to happen here when the compiler sees this code is the compiler is going to go, okay, the first thing I need to do, right, when I'm actually compiling this code, I'm going to actually try to sort of write out the compiler's thought process here, right? I have to load from the memory pointed to by from, right? It's got to go get that, right? It's got to actually fetch it. So it's got to generate an instruction that says go load this memory. Then it has to write that fetch into the memory pointed to by 2, right? That's what we told it to do. We told it to load out of this and write into this. That's all we were trying to do, right? Now you tell the compiler, basically, wait, did I do this wrong? Yes, I did this wrong. Sorry. There we go. Like I said, not a compiler optimizer, so I don't think about these things very often. Now we're going to say, let's go ahead and load. Well, even that's not right. This is such a simple example. You'd think I'd be able to do it by now. But some reason when I'm trying to explain things, it's hard for me to think in my head exactly how the things are going. Yeah, so it's always a bit of a nightmare, ladies and gentlemen. Oh, no, I'm right. Okay, good. Yeah. Bit of a brain fart. It's getting late. What can I say? Okay, so now we're going to go ahead and say advance the pointer to by how much? And you should all know this by now. It's not 2, right? It is actually 2 times the size of an integer, right? So it's actually going to advance it by 8, right? And then it's going to say, okay, I have to load from the memory pointed to by from, and then I have to write that fetch into the memory pointed to by. And at this point, we'll start to introduce maybe a little compiler stuff here. This is really not 2 anymore. In some sense, the compiler thinks of these things as separate values because we moved it, right? So it really thinks of it more like a new thing. It basically says 2, right? A second 2 becomes the pointer 2 plus 8, right? And so then it's going to write the fetch into the memory pointed to by 2, right? So we've got 2. This is an extremely simple function. And what is happening is we write into 2 different memory locations. That is what the compiler sees. It thinks there are 2 total writes, 1 to 2 and 1 to 2. No, that's a bad thing. 1 to, let's call it other. Or first and second. A and B. There we go. That's good. Just to avoid it getting completely out of control. Okay. So it's going to load the memory pointed to by from. It's going to write what it loaded into A. It's going to make a new pointer called B conceptually. And it's not really doing these things. It's just this is what it thinks it has to do. It makes a new pointer called B that is A plus 8 bytes. It's going to load the memory pointed to by from again. And it's going to write whatever it loaded into what's pointed to by B. Right? Does that all make good sense to people? Hopefully that is true. Hopefully people are following me so far. Pretty simple. Now, what you want the optimizer to do here, right? That is sort of like, if we just think of these as instructions, that is 5 instructions, right? I mean, who knows exactly what they translate into depending on the circumstances, but there's 5 logical things that have to happen here. It has to do a load, a write, it has to do an increment, another load, and then a write. Now, what you want an optimizer to do, and the whole point of an optimizer, is to look for things, oops, that did a very odd thing, look for things like these guys, these 2 guys right here, right? Do you see how both of these are the same thing? They are both loading the memory pointed to by from. And since from hasn't changed, what's the contents of that memory has not changed, right? And so basically what happens in circumstances like this is you want the optimizer to go, well, this second load I can just eliminate because I know what the value of from actually was, right? I know what it was. So I can just rewrite, I can replace this by saying write the previous fetch, the one from up here, into the memory pointed to by B. And now I have saved one instruction, essentially, one conceptual instruction at least, possibly even more instructions in the actual CPU, depending on how many it would need to do that thing. It has now saved those instructions. That is an optimization. That is what the optimizer does. It takes the literal thing that has to happen in your code and turns it into something more compact that does the same thing. Now, the compiler can't do that to this function. And again, when I say that, what I really mean is this is a simple example designed to show the kinds of ways that that can happen. And maybe the compiler actually can do it to this function. And like I said, you want to go talk to a real compiler expert to tell you the real intricate ways that this all plays out. But this is basically the idea. The reason it can't do that is because it doesn't know if from and to might point to the same place. So let's suppose that the shenanigans outside of this that we're calling the function, right, had an integer star blah, right? Let's say it did that. Let's say it goes ahead and passes the same pointer to do the stuff for both of these, right? Well, now what's going to happen is when it overwrites to, it's actually overwriting from, right? Does that make sense? Now, in this particular case, you're still okay, I believe, because since you read and wrote from the exact same location, you're probably fine. But you have to imagine the compiler doesn't actually know, like, let's say this continues on, right? It continues on and goes for more cycles. It keeps going and incrementing further. So basically you do something like that, right? So that it, in this case, like I said, it wouldn't matter if it was literally just doing it one because this would be the same value as it was going to overwrite. It would overwrite itself with the same value. But let's say it was just one ahead of itself, right? So it was reading, or two, right? So it was reading and writing right ahead of itself. So it was going to overwrite the value it was about to read. And just to make that a little bit more explicit, I realized I kind of pulled a fast one on you there. I will actually do it 100% accurate here for you, the full-on real case. Again, there's probably a simpler case, but I'm having trouble thinking it through because I don't think about these things very often from the compiler's perspective. And when I'm talking out loud, it's kind of hard for me to actually do them all 100% correctly. Okay. So basically, I'm going to do this, right? Like that. I am then going to go ahead and increment, let's say 2, like this. And then I'm going to increment from like this. And then I'm going to go ahead and do the same copy again. I think this would do it right. Let's double check that that's true. So now let's say I come in here, and this is the memory that I actually have. This is blah. Let's say blah is pointing to something like 10, 20, right? And I don't even need, why did I even bother with the 2? We can get rid of that. We can make it even simpler. All right, there we are. So basically what I'm doing now, if you can see, is I am creating something that's basically, let's say I have a pointer to a pointer blah here, and blah is pointing, it's pointing for whatever reason at this point in the program to 2 integers, right? The first integer is 10, the second integer is 20. Let's just say that's what happens, right? So let's see what happens when we actually run this, and hopefully I did it correctly. When I do the first *2 star from, well, what is star from? Star from is, and we want this way, right? Is that correct? So complicated. Why am I? This is basically the problem with streaming live. Is, man, you don't get a chance to think about these beforehand, and you're trying to talk it through at the same time. So I'm going to read from a value, and then I want to overwrite that value. Right. This is actually the way to do it. Okay. Okay. Yeah. We're writing. Yeah. So it's the value. You know what? This has been a disaster, ladies and gentlemen. This is the worst example that I've ever given. Basically, this should be a really easy thing to demonstrate how the pointer is alias. And for some reason, it is like impossible for me to construct a simple case, because every time I try to simplify it, I realize that I write something that technically should still execute properly because the copied value is actually going to be the same. So again, my penance for this is I really pretty much just have to stay here and actually give you a valid case. So bear with me for a second while I unclog my brain and actually try to write something that's going to be valid. So I'm going to try writing something called move, let's say. And move is going to take 2 pointers. It's going to take an int a and an int b. Well, I guess I'll stick with my from and my to, even though it was going so poorly. We'll do it that way, and we'll say one of them was const. And so what this is going to do is it's just going to literally do the copy, right? So it's going to do, it's going to do this. It's going to do basically this. It's just a copy function. So let's say it does this, and let's say it copies 4 integers. So it copies, it reads an integer, writes it, reads an integer, writes it, reads an integer, writes it, does something like this. And maybe when it does that, it writes the same, so it's kind of like a thing that, something like this. It's kind of a thing that actually duplicates the value out. In fact, I'll do this, make this a little clearer. We'll do it that way. Let's see if this can actually work. So basically, I am kind of overwriting the values there. That is what I expect to have happen. So I will overwrite that, and I'll increment from once. I think this will be enough to do it, but maybe I just did the exact same stupid mistake again. We'll find out. So now I have my pointer, and it's got 1, 2, 3, 4 in it, let's say. Some pointer in memory that's pointing to these things. So int blah points to those integers in memory, right? And then I call move, and I'm going to call move with blah. So I pass blah and blah. And what I want to do here is I want it to eventually overwrite from. So from is going to be, let's see, it's going to write to 1, then it's going to write to 2, then it's going to write to 3. So I'm going to say that it is going to point to blah plus 1. And let's see what this does if I have finally actually done it. You know what I just realized too? This is definitely an owl of shame moment. That should have been a really easy thing for me to write, and the fact that it isn't just shows that the owl of shame needs to make an appearance to let everyone know that this was not something that should have taken this long. This should have been like a 5-minute thing, and that is just basically, the shame owl makes its first appearance, and I strongly suspect there will be a lot more shame owls coming out in the future. As we get into more and more complicated code, it will only be harder for me to think it through live like this. I hope you will stick with me, ladies and gentlemen, and I do apologize for the delay. Anyway, off we go. What we'll actually do here is 2 is currently pointing to blah, the first element of blah. So if we look in here, after this instruction, right, this instruction is going to read from. From is pointing to the 2. So this reads a 2 and writes out a 2. So that's going to be 2, 2, 3, 4, right? Let's see what this does. This is going to read, let's see, from again, you know what, let's do that. I'm going to pass both the same ones. Okay, so this reads a 1 and writes a 1. No, that still doesn't work. I'm trying to think of the appropriate punishment for not being able to write simple pointer lists. I keep wanting to do it with a copy, but I can't seem to do it with a copy. So you know what? Maybe we just need to not do that case so that I guess maybe whatever my brain... Why does my brain even think that would happen? Because it should always actually work. I don't know. I'm just being stupid today. We'll try it one more way, and if we can't figure it out, then we will just call it for the night, and we will say that someday somebody who is thinking a little more clearly, or actually it'll just be me. I'll sit down for 10 seconds after the stream is over, and I'll be like, oh, right, duh. That is how that works. Anyway, let's say that we go ahead and do something with 3 pointers, maybe, something like that. And we say something like star A equals star B, star C equals star B, that kind of a thing. So we're going to write 2 things in there, and then maybe some interceding thing. We'll just get some more pointer reads in here so that we can check it out. So star D equals 5. The funny thing is, I think my example that I gave earlier in the stream that I just typed out in the middle of like the hyperness, I think just worked. So it's kind of hilarious that I'm having this much trouble with something that really should not have been a problem. But anyway, so this, yeah, and looking at this, this just works. Why did I overcomplicate things so much? I don't know. Ladies and gentlemen, you are free to basically point your own owl of shame at me if you have one at home, because this is simple and I believe this one just works, so it's kind of ridiculous that it took me that long to explain it. Here we go. We've got 4 pointers here. We are reading out of B twice. So this is load B, write A. This is load 5, write D, which you could probably do with the immediate, so it's probably just write D. And this is going to be load B, write C, right? Write to load from, like that, right? So that's all good. That's all well and good. And the only thing, this is the only thing you needed to understand pointer aliasing, and yet I spent probably 15 minutes of your valuable time trying to make a stupid copy do it for no apparent reason other than for some reason I really wanted to write it as a copy. So yep, well, you know, there you go. It takes 5 seconds to write the right thing and 15 minutes to write the wrong thing. I don't know how to explain that, but here you go. If now we have in memory, we're going to call this move function, right? And we have some things that we can point to. So we have a int x, an int y, an int z, and an int w. And I will just set these to 1, 2, 3, and 4. Okay, hopefully that is pretty understandable. Nothing particularly odd going on there. And so I am going to go ahead and pass this function x, y, z, w, right? And it should work 100% properly. There's nothing odd about that. It will go ahead and do the right thing, right? It will, if you look at what will happen to this program, it'll load from B, which is set to Y, so it'll load a 2 out of there, right? And it will write the 2 back to what is basically X, so X will become 2. It will write, excuse me, straight up it'll write 5 to W, which is fine. And then it will write to C, it'll write C, it'll write whatever was in B, which is 2. So you'll end up doing all that, and it will work totally properly. Now, in that circumstance, you could also see that if I wanted to, I could just load from B once, because the value that you load from B is always going to be 2, correct? It's always going to be a 2. So when it loads from B, it gets 2. It loads from B, it will get 2. It could just fold those out and say, write to C the same value you wrote to A, right? That is basically what the optimizer is going to do. The optimizer is going to say, hey, look, all I need you to do is load from B once, because since you're loading from B twice and the value isn't going to change, it's just B the whole time, right? I can just save that. And that is the optimization that it wants to make. Now the point is, it cannot make that optimization. The reason it cannot make that optimization is because there's other pointers here, right? And that is a problem. What it doesn't know is whether 2 of these pointers alias. And if 2 pointers point to the same memory, they are called aliasing. So let's say I go up here, right? And because I am being mean, I set B and D to point to the same place. Well, now, when you read out of B here, right, you will get a 2. But when you read out of B here, you should have gotten a 5, because the interceding write to D wrote a 5 into the location that used to contain a 2. So the compiler cannot optimize this away. It cannot write to C the same value it wrote to A. It has to, it must always load from B. It must, and then write to C. So pointer aliasing, right? Pointer aliasing is basically, pointer aliasing is when 2 pointers point to the same memory, or rather 2 pointers could point to the same memory, and the compiler doesn't know if a write to one of those pointers might affect a read from the other pointer, right? That is the key. It doesn't know whether it can optimize out that second load from B, because it doesn't know if you might have just written a 5 in there. So really there's 2 ways to interpret this code depending on whether the pointer's alias. One is that you can load from B once and write it twice, and one is that you can load from B twice, or rather, load from B once, and then write a 5. Because you would know that the only thing, the optimizer would know the only thing that could happen was the 5. But it doesn't even know how to make a determination between those. It'd have to actually compare the pointers, and that would be slower than probably just doing it. Than just actually doing the load, potentially. Because it still has to do the load. Well, maybe not. I don't know. It could do that if it was really smart. I'm not sure. Possibly not. But anyway, you get the idea there, right? Hopefully that makes some sense. So basically, what you need to understand is anytime you pass pointers, the compiler can't really do any optimizations with those pointers if you write to them. If you only ever read from them, you're usually fine, because it's only the writing that creates something that could happen. If this write to D weren't here, then there's no other reason that B could get changed. Now, in a threaded environment, you may see things like this, where people put volatile on something. And that's a way of telling it that some other thread could be modifying stuff. But assuming that you're working with code that is guaranteed to be single-threaded, which is what you're doing when you don't put volatile, when you're just telling the compiler, hey, these are just regular variables that only my thread touches, or I know that all other threads are locked from not touching those variables at this point in time, then it goes ahead and assumes it can optimize those out so long as it can tell that nothing else. So basically, in this circumstance, what you want to do, right, is you want to pass B by value so that you can tell the compiler very clearly, look, you don't have to worry about reading from B as an address. I'm telling you what the value of B is up front, and so you know that it can't be changed by this interceding write to D, because there's no way to get an address to this parameter, right? That's not possible. Does that make sense? Hopefully that makes some sense. I apologize for the long-winded and completely useless copy example that I was trying to construct for you that I thought was going to be more fun. It was just a world of hurt. But that is basically all we're talking about here. There is really nothing more to it than that. It is extremely, extremely basic. Now, basically, the kinds of optimizations that happen are obviously much more complicated than this, and the kinds of pointer aliasing that happens can be much more complicated than this. So this is a very, very simple example. But that sort of thing can happen all the time as you're passing pointers around. The compiler constantly has to be aware of what could happen there. And so that's a very important thing to understand when you're actually trying to do optimization. So I'm sorry that that took so long. That should not have taken that long, but that is just the way it goes sometimes. So it looks like we are done with questions. So that is good. We are down here at the end of the stream, so that is pretty cool. Let's see here if there's anything else. Yes, and I'm terribly sorry for that, such a long-winded explanation. Again, like I said, you got to bear with me on the stream sometimes. It's also a learning process for me in terms of trying to keep my train of thought correct. And talk at the same time. It's actually really pretty difficult because talking and coding kind of use the same part of your brain, so it's a little bit difficult. So sometimes my explanations go a little bit long-winded. I will stick them out every damn time. So I just ask that maybe you stick them out with me. I realize it's a little frustrating because it's way better if someone can just give you a real concise example and not have to muddle through it, which we have done a number of times on the stream, so we've been getting better at it. It's totally true, but we got a long ways to go because that was pretty rough. That should not have taken 10 minutes or whatever it took. That should have been a quick one. Let's see here. Is anyone posting notes from these casts? Yes, we will be putting up a website very shortly with notes from the casts. And so I hope that you will take a look at that. I will be announcing it on the live stream as soon as it is ready. It's not quite ready yet, so hopefully we will have some of that going. I was under the impression that the stack always grows downwards on Little Endian. Is that not true? I thought that it did as well. That was my assumption. But to be honest with you, I have done very little. I have never written a single assembly language only program in x64, which is what we're compiling in. Like on x86, I believe it always grew downward, but on x64, for all I know, they could have changed it. I mean, I had no idea. So I figured, well, I might as well check. I've never had to actually think about that. And so I just felt like it was kind of fun to check. So yes, I think it always does grow downward, and it continues to grow downward in x64, so that is good. You don't have to remember that it switches or anything like that. But I wanted to verify that. Let's see. Can you post interesting emails to get to the site? Yes, I will try to. I don't necessarily want to post emails exactly because people probably don't want their emails posted if they haven't actually said that they're okay with that. But what I will do is I will comb back through the emails I have received and make sort of a FAQ from them that sort of discusses things that people have asked me and what I've answered. Clemensbaum, the compiler is allowed to and actually does assume that two pointers to different types never alias unless one of the types is char or unsigned char. That is correct. Basically, there are modes that you can put the compiler in. And so there are optimization modes you can put the compiler in that make it assume a bunch of things about aliasing. And I find, in fact, a lot of people, in fact, I think even Rad does this now by default, turn those modes off. And the reason is because they are bugs waiting to happen. Compilers are now assuming more and more stuff about aliasing, sometimes in situations where you really, really don't want them to. And so assume no aliasing is a really bad thing in compilers, and I think we want to kind of get rid of it. What you'd much rather do is mark up your stuff to say when things don't alias. Honestly, I think that should have been the default. Unfortunately, the language support for it is a bit spotty, but there are things like the restrict keyword and the assume keyword that you can use. And so that is kind of it's kind of a bit of a messy situation, and we will definitely probably deal with that a little bit later. Win32 display buffer in Windows is taking 4 unused parameters. WM-Paint is the only part where we pass those, but we never use them. Will that change? You know, I'll be honest with you, I don't know if we really need to worry about dirty rect updating. It seems like kind of a waste of time. So we could easily just go ahead and say that we are not going to do that. We could basically say that we just don't care about what the dirty rectangle is, because for the most part, since we're going to have to update the whole screen every frame anyway, we must be able to do that quickly. So we could easily just say this is the new thing for the program, and that would be fine, I think. So let's go ahead and double check that that's all good. So I think that's probably fine. Those are just, we had passed those because WM-Paint does actually give us back the rectangle that we need to refresh, so you could save a little time by only refreshing that region, but since we know we have to blit the whole screen at 30 frames a second to make a game feel good anyway, we can pretty much assume that we don't need to do that and simplify that code, because obviously we don't need to just worry about a small rect on Paint if every frame we have to repaint the whole thing anyway. Yeah, so that's fine. It's a good point, and the answer is no, you do not have to worry about those. Wouldn't it be better to keep comments in the code about the explanations you do? Sometimes yes, sometimes not. I'd rather maybe pull those out to the forums, because honestly, if the code gets too cluttered up with comments that are explanations, and especially if those explanations are no longer pertaining exactly to the thing because we changed the code a little bit, that's going to get annoying. So I'm going to try not to do that, probably. All right, it is 10 p.m. here, ladies and gentlemen, so let's go ahead and wrap this up. Let's do one last code question. Why have bytes per pixel as a variable? Do you expect it to have different values? Why not put it as a global cost define, or even replace it with BMI header.bi bit count divided by 8? Those are all good suggestions. I would be okay with all of that. Every last one of those is totally viable. I just found that it was kind of a nicer thing to put there because it's kind of all the stuff that actually you need to know about the on-screen buffer, so I just felt it was kind of a nice thing to put there. So I don't see any real reason to remove it, but we could just change that back to a local variable. So, you know, we could totally do it this way. We could say this, right? Go back to the way that we had before and just say that it's always that, because really we're not going to handle anything else, so that might be the right way to go. I do not know. We could totally do that. We could totally do that. Let's think about it. Yeah, let's go ahead and do that. Let's just go ahead and say, for now, because we can always change our mind, let's just always say pixels are always 32 bits wide, little endian, like that. Although maybe I'll say memory order, BBGGRRXX. There we go. All right, everyone, thank you for joining me. Hopefully that cleared up everything that we were doing. Let's see here. Yeah, that looks good. To the person who said, ugh, make it const. though maybe we should take one more thing. Someone was grumpy that it wasn't const. I never like to use const. Const is basically the only thing const does is it basically allows the programmer to potentially not make mistakes if they were to assign to it. So basically, if you type in const, it just means that you can't type bytes per pixel equals 8 here, right? It will give you an error. It'll say that you can't assign to a const variable. I don't find them to be useful at all. I have never had a bug in the 15 years since I stopped using const. I have literally never had a single bug that would have been caught by it, so it is just a waste of typing for me. It may not be a waste of typing for you if you make that mistake often, but otherwise it is completely useless, and the reason that it is completely useless, except for a small number of cases where you're defining global variables and need to say, and you don't want to use a pound define, for example. The reason that it's completely useless is because the compiler cannot actually assume that something that is called const is actually const. In any case, const is actually so meaningless that const does not even exist in the optimizer. In fact, if you don't believe me, Chandler Carruth, who I mentioned before, go watch one of his lectures. You will find him explain the fact that const is completely useless and does not even exist in the optimizer. It does not even use const. And the reason for that is because in C++ they allowed you to cast away const, which means that something that is const does not actually have to be const at all. And so basically what happens is you get into situations that look something like this. Basically you have somebody who's doing, do the stuff, right? And it's got int const A and int star B, and it could just as well be the case, just because you said that these were constant, well, for all it knows, B could also point to A, right? It's that aliasing thing all over again. So the fact that this is called const is meaningless because the optimizer has no idea whether B actually secretly does point to A, and so if there's a write to B here, that could be mutating A. So const is literally useless. It has absolutely no use whatsoever to the compiler, and if you don't believe me, go ask Chandler, go ask someone who works on an optimizer. It does not help. It cannot be propagated down. So const is useless, but if you find it useful for your own coding practices, you can go ahead and use it. That is fine, but just don't think you are making better code by adding const, because that is not true. It does not help you. All right, guys, that is the end of the stream. Thank you all for joining us. It was a bit of a meandering Friday, but I wanted to go through all this stuff with you, make sure everyone was comfortable with everything we did during the week. Next week, we'll be starting again on Monday at 8 p.m. Pacific Standard Time. Next week, we will try to move Friday to an early time so that people in other time zones can watch. So we will do Monday through Thursday at 8 p.m. as usual, and then on Friday we will try to do something perhaps in the morning or something that will be at a time when other people in other time zones can tune in live, because a lot of people have been asking about that. So we will go ahead and do that. I will try to post a schedule for you, and hopefully we'll have that website up too, so I can have a place where the schedule always lives, and you can find out ahead of time when this will be aired. So, thank you all for joining us. Next week we will tackle input and sound. Assuming that we can get through them both, we will try to tackle sound first, and if that takes all week, then we will do input the week after. It is Thanksgiving week, but I still plan to be streaming, so I hope you guys can tune in and join me. If not, have an excellent Thanksgiving. Those of you who are in the US, I guess, I don't know all the countries that celebrate Thanksgiving, but we celebrate it here. Obviously, it's kind of an American holiday, so it probably isn't celebrated much outside of America. But for those of you in the U.S., have a happy Thanksgiving next week if I don't see you on the stream. If I do, we'll eat turkey together and program sound on Windows. Thanks, everyone, for joining us, and I will catch you next week.